Hello everyone, my name is Logan and welcome back to the lecture hall. For today's video, we are covering 11.9, representing functions as power series. So, well, we're going to begin with a function that we've represented with a power series multiple times without even fully knowing it. We have 1 over 1 minus x. What is this? Well, this is the formula for the equation for a geometric series. So this is what a geometric series is going to equal, assuming x is less than or equal to 1. Well, what is that? It's going to be 1 plus x squared plus x cubed plus blah 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 all the way to infinity. And this is just going to equal the sum from 0 to infinity of x to the n when x is less than the absolute value of 1. So now, what if we have 1 over 1 plus x squared? What is that going to be? Well, we can actually rewrite this somehow. Well, what's going to stay the same? Well, this 1 is going to stay divided by 1, and then we're going to say, well, let's try to get it as close to this as possible, because this whole section is about trying to get something of the form like this, depending on what we start with. So we have 1 over 1, well, we want a minus, so let's make it a minus. And then we're like, well, this is a minus x squared. So this would kind of look like this if we then made this a minus, which we've done, and then made this an x squared instead of an x. So, well, what is this going to be equal to? This is going to be then equal to the sum from n equals 0 to infinity of, well, now it's just negative x squared to the n, which is then going to be equal to the sum from 0 to infinity of negative 1 to the n times x to the 2n. And this would be the power series representation of 1 over 1 plus x squared, and that is going to be equal to the sum from 0 to infinity of negative 1 to the n times x to the 2n. Now we are going to cover the only theorem from this video, and this is a very powerful theorem. So let's suppose that f of x is actually represented as a power series, and it's the sum from 0 to infinity of c to sub n times x minus a to the n, and has a radius of convergence equal to r greater than 0. Then f of x is going to be differentiable, and if it's differentiable, then it's going to be integrable as well. So f of x is going to be equal to this c0 plus c1 times x minus a plus c2 times x minus a squared, blah, blah, blah. And this is represented as our notation we've already mentioned. Now, if we take the derivative, well, now f prime of x is going to be equal to c1 plus 2 times c2 times x minus a plus 3 times c3 times x minus a squared, and so on and so forth to infinity. And our new power series representation is going to be the sum from 0 to infinity of n times c sub n times x minus a to the n minus 1. And now for our integral, if we took the integral of f of x with respect to x, or the integral of f of x dx, this is going to be equal to big C, our constant that we have to add for any integral, and then big C plus c0 times x minus a plus c1 times x minus a squared divided by 2 plus, and so on and so forth to infinity. And this is going to be equal to big C, our initial constant, plus the sum from 0 to infinity of c sub n times x minus a to the n plus 1 this time, all divided by n plus 1. And so why is this important? Essentially, this makes it so that we can know for certain, yes, we can take derivatives and integrals of power series, and they're incredibly easy to take integrals and derivatives of because it's just the power rule. So now we're going to apply this to a function. What if we wanted to find the power series representation of tan inverse of x? Let's get into it. So, if we had the function tan inverse of x, and we wanted to find the power series representation of it, how would we do that? Well, let's think about it for a sec, and we also know that we can use integrals and derivatives with power series. So, then we're like, let's see. Well, we know that the derivative d dx of tan inverse of x is going to be equal to 1 over 1 plus x squared. Where have we seen that before? Well, we've seen it about 5 minutes ago when we were trying to represent 1 over 1 plus x squared as a power series. Well, this is going to be equal to the sum from 0 to infinity of negative 1 to the n times x to the 2n. And this is going to converge, we didn't know, when x is less than or equal to 1. And then we're like, okay, well, if this is the derivative equals a power series, we can just integrate said series. And we can actually, we have to write our dx. And so this is then going to be equal to the sum from 0 to infinity of the integral of negative 1 to the n x to the 2n dx. And so all we have to do is integrate term by term, and this is going to then be equal to the sum from 0 to infinity of negative 1 to the n times x to the 2n plus 1 all divided by 2n plus 1. And so what's our final conclusion? Well, tan inverse of x is actually equal to the sum from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1. So that is all I wanted to cover in the lecture portion of the video. Let's transition to some practice problems. Let me see here. I don't know if the camera can see this. Yeah. So we're going to do one question, and that question is number 5 from our textbook. That is going to be 2 over 3 minus x, and we want to represent it as a power series function, and we want to find its radius of convergence and interval of convergence. So let's do it. Let's mess with this 2 over 3 minus x. Well, 2 over 3 minus x, that's equal to 2 times 1 over 3 minus x. We know that. And then we know this is actually going to be equal to 2 over 3 times 1 over 1 minus x over 3. And then we're like, well, we know the stuff of this form, 1 over 1 minus x over 3. Well, this is going to be equal to, then, 2/3 times the sum from 0 to infinity of x over 3 to the n, which is then just going to be equal to the sum from 0 to infinity of 2 times x to the n over 3n plus 1. How do we find its radius of convergence and interval of convergence? Well, that is a quick ratio test. So that is the limit as n approaches infinity of a to the n plus 1 over a to the n, or a sub n I should say, and a sub n plus 1. So this is absolute values of 2x to the n plus 1 over 3 to the n plus 2. Now times, we're going to say times because we divide, and when we divide we multiply, or flip them, multiply. So then this is going to be 3 to the n plus 1 over 2x to the n. And, well, what does this simplify down to? We can get rid of our 3 to the n plus 1 and cancel out with this n plus 2 power. What's left? Just 3. And then we cancel our 2's, and then we can get rid of our x to the n and then the n plus 1 powers, and all that we have left is now just the absolute value of 3 over, the absolute value of x over 3. And we want that to be less than 1. Why? Well, because that is how we find our radius of convergence. So when that's less than 1, that means the absolute value of x is less than 3. So then we get that our radius of convergence, our ROC, is going to be equal to 3. And then we need to find its interval of convergence. Well, we know our interval of convergence is going to be equal to something 3, 3, negative 3 and positive 3, and we just need to see if they are going to be included or not, so hence parentheses or brackets. So let us do that. So if we set x equal to 3, well, we just plug in 3, and this is going to be equal to the sum of 2, and then 3 to the n over 3 to the n plus 1. And well, what does that then equal? This 3 to the n and n plus 1 cancel, and this just equals the sum of 2/3, which we know is divergent, because it's just 2/3 over and over and over again. So what do we know? Well, at least our upper bound on our interval of convergence, that's going to be a parenthesis because 3 is not included. Next, we try x is equal to negative 3. Well, this is then equal to the sum to negative 3 to the n over 3 to the n plus 1, which is then equal to 2 times negative 1 to the n over 3 to the n over 3 to the n plus 1, and with a sum notation, of course, and then we can get rid of our 3 to the n and 3 to the n plus 1 and just have a 1/3 left over. And so we then get an alternating series from negative 1 to the n times 2 over 3. And so what is this going to be equal to? Well, the series, or the sequence goes negative 2/3, positive 2/3, negative 2/3, positive 2/3, negative 2/3, positive 2/3. So that bounces back from, it goes from 0, 2/3, negative 2/3, and so it never actually slows down on one place. So then this is also going to be a divergent series, because it never converges, and so we can say that our interval of convergence is both parentheses. So it is from negative 3 to positive 3 without including those 3's, i.e. x has to be greater than, x has to be less than the absolute value of 3. Or I guess the absolute value of x has to be less than 3. That is all I wanted to cover in today's video. As always, my name is Logan. Thanks for watching. Have a great day.